Hi students, welcome back to another lesson from Vernon. Today we will be talking about lesson 5.2, which is our proof lesson. Now you're going to find that 5.1 and 5.2 have a lot of similarities in what we do. We won't add any new identities, and really you're going to see that simplifying built into doing a proof. So a couple big things related to proofs that you should know are the following. Our objectives for every single day of these lessons will always be, you want to simplify to show that the left-hand side, I'll refer to the left-hand side as LHS, is the same as the right-hand side, which I refer to as RHS. The second objective of the day, and again, this one will follow through, is I understand the rules around how to prove something is equivalent. And so we're going to go ahead and start up with some proofs. But before we do so, we just have a couple quick reminders. So with a proof, the whole idea of a proof is that it should be easy for us to see the equivalence. So whatever you do, it should be easily seen to be equivalent to the preceding one. So therefore, if I'm doing my work, if I skip a step or if I do two steps in one, it isn't easily visible. Therefore, we might say, you know what? I can't understand your work, and so I can't give you credit. So be really mindful that when doing a proof, you must show that the steps are easily equivalent to the preceding one. When completing a proof, you want to know that you cannot move things or terms from one side to the other. So you don't want to be balancing. A proof is simplifying one side to look like the other side. And last but not least, you must always show your work in the order. Otherwise, it's difficult for us to see what is going on in the process. Okay. So we're going to start off with an algebraic proof. I find that sometimes these are easier to wrap your brain around, and then we'll move into the trig proofs after this. We're only going to do one example of an algebraic proof. In this particular algebraic proof, we are showing that the left-hand side, and I'm just going to denote that by underlining, this is everything on the left-hand side of the equal sign. We want to show that that is equivalent to the right-hand side. So basically, there's nothing I can do over here. So I'm only going to be working on the left-hand side. Now, when I go through my proof process, I like to give you the reason or kind of use this column to show my work. I might do some expansion depending on the type of proof I'm doing. So just kind of know that this column is not necessary, but it's necessary in order for me to teach you well. All right, let's go ahead and take a look at the proof side of this. So when doing a proof, you want to work on the side that is more complicated. So it's very clear to me that this is the more complicated side. There's not really much I can do with the number 2. So as I look at this, I'm like, okay, I could get a common denominator, but then I'm going to deal with cubed terms. Might not be as effective. But I noticed that this top is what we call a difference of 2 squares. So a difference of 2 squares, if you remember, is the one where it factors nicely. So if I had like a squared minus b squared, we would say this factors to a minus b times a plus b. And this always happens when you're subtracting and you have a perfect square as your 2 terms. So what this means for this problem is I can factor the top to x minus 1 times x plus 1. And the bottom of that first fraction stays the same. And in the second fraction, again, it's the same term on the top. So I'd have x minus 1 times x plus 1. And on the bottom of this one, I had x plus 1. Now, if you would have chosen to go ahead and try to get a common denominator, it would have worked out, but it might have been a couple extra steps. From here, I can now simplify my fractions. So on the first fraction, the x minus 1 ends up dividing out, and on the second fraction, the x plus 1 ends up dividing out. So in that reasoning, I'm just simplifying. Now, as I go ahead and move on to writing the next line, I notice that I have a minus sign here. Be really careful with this. That minus sign needs to be distributed into both terms that come into that second part or that second fraction. So when I rewrite this, now I don't need parentheses. I can say x plus 1 minus x plus 1. And the reason it changed to a minus x plus 1 is because I distributed the negative that was in front through. Now, as you can see, we very quickly have simplified this problem down, making it a lot more reasonable to work with. At this point, I see that positive x and negative x equals 0, and 1 plus 1 equals 2. At this point, I have successfully shown that the left-hand side is equal to the right-hand side, and notice I've only worked on one side of my proof at a time. I usually like to end my proofs with a nice big smiley face. It just makes me feel really successful, like, yes, I did this. It makes sense. I understand. And so again, the last step, this reasoning column is really just meant to help you understand what I mathematically did as I worked through the proof. Awesome. Let's move on to the next example. All right, in the next example, I'm actually having us do a little exercise. So because we can only work on one side at a time, it's essential that we can simplify well. And what it means to simplify well is being open-minded and flexible with our thinking. That's really hard because in math, we like to think there's only one way, there's one process that will work. And that's true. However, sometimes when doing that process, it's important to be flexible and think outside the box or think from a different perspective because it will make doing the problem a little bit easier. So in this exercise, all I'm asking you to do is I want you to figure out how to simplify these two statements. They're the same statement in two different ways. And I'm going to go ahead and start with the first one because we learned when simplifying that it sometimes is easier if we rewrite everything in terms of sine and cosine. Some people find that when simplifying this, they would rewrite this as sine of x over 1 divided by sine of x because cosecant is the reciprocal. And then they rewrite this side as cosine of x over 1 over cosine of x. What they've done is they've created a complex fraction. Well, we can simplify a complex fraction by multiplying the top and bottom by the reciprocal of the bottom. And so what happens is the bottom is now gone. It equaled 1. And on the top, we have sine x times sine x, and this is over an invisible 1. So we end up with sine squared of x. And what happens on the other side, again, doing that same process, I'm multiplying by cosine of x over 1, or the reciprocal of the denominator. We end up getting cosine squared of x. And we know that sine squared plus cosine squared equals 1. This is one of our Pythagorean relationships. All right, not so bad, but I'll be honest, sometimes we get a little bit mixed up when we're doing this, simplifying a complex fraction. So let's look at another perspective on this. Another perspective on this is if you recognize that there's an invisible 1 in front of the sign, or I could put a 1 in front of it, you might recognize that we have 1 over cosecant. And 1 over cosecant is just sine x. And we can do the same thing with the other side. I have an invisible 1, and 1 over secant is cosine. And the cosine on the top stays put. And now we get sine squared of x plus cosine squared of x. Now you might say, well, Ms. Vernon, that's exactly the same thing you did over here. But it's not. It's a little more simple. And again, just being open-minded and being able to think outside of the box will help you create a more easy to follow proof as you move through this process. All right, let's go ahead and take a look. I have one more example for you today. Again, don't worry if you're feeling a little overwhelmed. Proofs typically will cause that to happen. Stay with me and just keep doing the practice. It will pay off. So before going into our last proof, I just want to remind you, we're only using these identities. And then I've also included a quick trig proof tips and tricks list that we will continue to build as we do these lessons. So the first step I highlighted in our initial introduction, always begin with the more complicated expression. You should know that adding and subtracting is more complicated than multiplying. So be mindful of that. Second tip I have for you is if you are unsure where to go, try changing everything into sines and cosines. This doesn't always work, but oftentimes it gives you a nice starting point that will help you get through the process. And my third tip for you is combine fractions by getting a common denominator first. Remember, we need a common denominator whenever we are adding or subtracting fractions. All right, let's jump into that final example. So in example 2 of our processing here, we have use your identities to prove that tangent of x plus cotangent of x is equal to secant of x times cosecant of x. So in doing so, I'm going to start the process off by highlighting the term or the side of the problem that is more complicated. In my opinion, tangent of x plus cotangent of x is the more complicated expression because it involves adding. Okay, so we are going to work the left-hand side of this particular proof. Now again, our starting off point, this is what was given to us. We used that same terminology in the past. And I'm going to begin by rewriting these in terms of sine and cosine. I'm going to take that tip that we learned. So we are identifying the more complicated side. Then we're going to change it into sine and cosine, mostly because I need something to do and these aren't being squared, so that's really my only option. So in turning this into sine and cosine, I would have sine x over cosine x, that's what tangent is equal to, plus cosine of x over sine of x. I am not going to write down the right-hand side each time because it just becomes a lot of extra writing. And really, we want to focus on one side at a time. So I used the quotient identities. So if you're looking at what is she doing, I'm using those quotient identities from our identity sheet. Well, now I see that I have two fractions, and I'm thinking, two fractions, common denominator. That was one of our tips as well. So I'm going to go ahead. Let me go ahead and change that. I'm going to go ahead and multiply the left-hand one by sine x over sine x, and the right-hand fraction by cosine of x over cosine of x. This is a legal move because the orange terms are both equal to 1 if I were to divide them out. But in this particular case, they're very helpful because they allow me to get sine squared of x over sine x cosine x plus cosine squared of x over sine x cosine x. Now again, I'm not going to rewrite this, but what did I do? I got a common denominator. All right, so at this point, because I have a common denominator, I am now able to write this as a single fraction. And so in writing this as a single fraction, I'm going to write just my sine x cosine x on the bottom. And on the top, I notice that I get sine x plus sine squared of x plus cosine squared of x, which is an identity, and that equals 1. So this is your Pythagorean identity, sine squared of x plus cosine squared of x equals 1. Now, you might say, Ms. Vernon, I don't see it. How are we supposed to get this back in terms of that? But because these are being multiplied, we can think of this kind of in two ways. One way is 1 over sine x. So this is like, that is equivalent to cosecant of x. And 1 over cosine of x is equal to secant of x. Now, my question to you is, does it matter that I have them written in the reverse way? And hopefully you're answering, nope, that doesn't matter. Multiplying two terms together still produces the same answer. Now, I want you to give yourself a little bit of breathing room and processing space. Go back and look at these examples. Don't get too overwhelmed. We'll do a lot more practice and a lot more examples to help you understand this better, but just give it time, and I promise you it will start to make more sense. Have a great day.